We've been talking about rotational motion, and we've covered torques and the rotational version of Newton's second law. What's left is to talk about the rotational versions of energy and momentum. So we'll start with energy and rotational motion. So, when an object is rotating, its parts are moving, and we know that there's energy associated with motion. We call that kinetic energy. So a rotating object has kinetic energy. This is, if the object is spinning in place, then it has kinetic energy because it's rotating. If the object also were moving while rotating, like if you throw a baseball and it's spinning plus it's moving, then there's two kinds of kinetic energy. There's the kinetic energy it has just because it's flying through space, and then also it would have the kinetic energy because of any rotation it has. So for now we're just going to talk about the rotational part. So we're going to think of objects that are spinning or rotating in place. They're not also moving. Okay, but yeah, so rotating objects have kinetic energy. And so what you have to do is just take all its parts and add up all the 1/2 mv squareds of all its parts. I mean, literally, perhaps literally at the level of molecules and atoms. You add up all the 1/2 mv squareds of all the pieces that are spinning around. Just to draw a picture, right? So we have an object that's pivoted at one place and it's free to spin around that axis. So every little bit of it, is moving, and therefore has kinetic energy. Okay, but of course we realize, so one thing is we don't want to have to literally add up 1/2 mv squared for all of the molecules of the object. We'd like a more practical way to compute the total kinetic energy, and there is. And that's when we realize that every object, every part, every molecule, every atom has a different V. And we talked about this before, right? It depends on how far away you are from the axis of rotation. And the further away you are, the closer you are to the edge, and the further away you are from the axis of rotation, you'll be spinning faster than points that are maybe very close to the axis. They won't be going as fast because they don't have to go as far around in the same amount of time, right? And in fact, we know we have the relationship that v is r times omega. That's the connection between your angular speed, which is the same for everybody, and the actual speed, which is different for everybody. Kinetic energy needs actual speed, but what we can do is replace v with r omega for all the pieces. So now my 1/2 m1 v1 squared becomes 1/2 m1 r1 squared omega squared, and the same thing for 2 and 3 and so on. So now that's what we're adding. Now that looks like I made it worse, but now what I can do is well, they all have 1/2s, and I can factor that out. But now they also all have omega squareds, which, remember, that's the same for all parts of the rotating object. They have the same number of radians per second that they're rotating. And then what's left is m1 and r1 squared, and m2 and r2 squared, and so on, because those parts are different for all the different parts of the object. But if you look what we have here, m times r squared added up over all the pieces, that is actually the moment of inertia. That was the definition of moment of inertia. So the kinetic energy ends up being equal to 1/2, and then this whole big mess just becomes I, and then we have omega squared. So there you go. That's the simpler, that's the simpler formula for kinetic energy of a rotating object. 1/2 I omega squared. Now, in a way, we're cheating because we're just hiding all the difficult part inside the I. But as you've already seen, for nice geometric objects like spheres and cylinders, calculus comes to the rescue and can give us the I, even though we didn't get into the details of that. So we're going to assume that in cases that we'll care about, we will have the I, and then this will be the formula. So that's something we can work with. So now this is rotational kinetic energy, and just to put this on our list in terms of the analogy of old stuff with new stuff, right? So we had, first of all, our kinematic variables x, v, and a. We now have theta and omega and alpha. Mass is now replaced with moment of inertia. Force is replaced with torque. And k, well, I want to be very clear. We're not replacing k. It's not like we have an analogous thing to kinetic energy. Kinetic energy is kinetic energy, and it's just that we had the kinetic energy because something's moving, and now we have kinetic energy because something is rotating. And they have different formulas, I know, but they're both still kinetic energy, whereas force and torque are not the same thing. They're just analogous to each other. Mass and moment of inertia are not the same thing. They are analogous to each other. And all of these are all analogous. But K and K, that's why we're using the same letter. It's not a new concept. It's just a new situation that we're applying it to. And so rotational kinetic energy is kinetic energy. So it's measured in joules. It's got the same units. It is kinetic energy. That's important to realize. The other thing I want to point out is, just like we had Newton's second law is F equals net force equals ma, and then we had net torque equals I alpha, and all the analogous pieces match up perfectly. Force gets replaced with torque, mass gets replaced with moment of inertia, acceleration gets replaced with angular acceleration. Well, in our new formula for K, it's the same idea, right? So we had 1/2 mv squared, and now for rotation we have 1/2 I omega squared. M gets replaced with I, right? Those are the analogous things, and V gets replaced with omega. So again, it's like these formulas that we're coming up with are translating nicely according to our dictionary here of variables and their corresponding rotational variables. So I just wanted to point that out, that this 1/2 I omega squared corresponds nicely to 1/2 mv squared. Okay, here's an example. What is the kinetic energy of a disk, and we have its radius and we have its mass, spinning around its center with a period of 0.050 seconds? Okay, so here's a picture, just a disk spinning around. So we want the kinetic energy, and we use our new formula, 1/2 I omega squared. Now we have to get I, and we also have to get omega. Well, I, we're talking about a disk here, and so we look up on our table of moments of inertia that the moment of inertia of a disk is 1/2 mr squared. I know that kind of has the same form as our kinetic energy formula, but that's, in a way, that's just a coincidence. Okay, so that ends up being 0.0026, yeah, 27, I should say, 27, two significant figures, kilogram meter squared, after you plug everything in. Now omega. So we do have to compute omega because we weren't given omega directly. We were given its period. So we know that t is 0.050 seconds. And we have to convert that to omega. So frequency is 1 over the period. So that ends up being 1 over 0.050 seconds, or 20 hertz. Okay, and hertz is really revolutions per second, and then, or rotations per second, and 1 revolution is 2 pi radians, so we can multiply by 2 pi to get 126 radians per second. Whoops, so that's the omega. I should kind of draw a line here. 20 revs per second, or hertz, was the frequency, and then when I do the conversion, now it's omega. Now it's in radians per second. So there's my omega. Okay, so now I'm ready to complete the calculation. So K is 1/2 times 0.0027 kilogram meter squared times 126 radians per second squared That's 21. Two significant figures. It's 21 joules. So that's how much energy this disk has just because it's rotating. 21 joules. All right. I'll break up this video, so I'll stop here for this part, and then I'll pick up in the next video.